Will Thompson is a senior test engineer in FormFactor's characterization lab. He joined FormFactor after completing his MSME at Stanford University after obtaining his BSME at Temple. Prior to becoming an engineer, he's earned a separate bachelor's degree majoring in business management and economics. So please welcome Will. Take it away.
Thank you. Thank you. Okay. I am Will Thompson from FormFactor, and I'll be talking to you today about die and probe layout strategies to enable probing best practices for heterogeneous integrated products, or HI products. And we'll start today by talking about industry's call for KGD from wafer and die singulated test, which we'll call probe or probe test. We'll get into talking about microbumps, which are the fine pitch structures that enable HI products, and as well as about how probe cards are set up to deal with those challenges. Then we'll get into specific BKMs on layout strategies. We'll talk first about a hybrid bump and probe layout strategy, and we'll also talk about using test pads among the microbumps. And finally, these will kind of hammer home that this is not just two specific examples, that we're also trying to kind of weave a theme that the optimal use of probe often involves compromising different test goals for cost savings in order to maximize the ROI of your probe test. Now, each HI product contains multiple chiplets, as we all know. And if, let's for example, say that we have 10 chiplets in a packaged good, and each one of these chiplets has a 90% yield, then you would only have about a 35% yield in your final packaged good. This arithmetic of composite yield loss has led to fervent and increased demand for higher fidelity from probe tests. In fact, chip manufacturers are asking probe to provide 100% verification of fault-free die, which is also known as KGD. And we like to hold this as an ideal, but as you'll see today, it's often economically unfeasible. The biggest reasons for it to be unfeasible are it's unfeasible sometimes economically, even for a classical monolithic die. And the two reasons are hardware and process time. From a hardware perspective, to run a full speed, full power test while physically touching each bump is going to require an expensive and complex tester and a costly and complex probe card. And then from a process time point of view, to perform the KGD test, it will take test time. And that means that the throughput of your expensive tester and your expensive probe card is now low, which is a massive ROI hit. So it's important to remember why we do wafer test at all. Wafer test is inherently a cost-saving process or product. The goal is to prevent downstream scrap costs. And so there is an upper threshold on how much you should be willing to pay per probe, that upper threshold being the downstream scrap cost. Therefore, it's important to decouple the bump and probe pitches from your designs. So as you'll see, and when we talk about microbumps, the demands from increased density on bumps is getting smaller and tighter all the time. And the way to keep your ROI of probe higher is to often sacrifice your goals of KGD in order to keep costs down and keep the ROI high. So about the microbumps, while many of you are familiar, I'll explain a little bit at a high level that the microbumps are the high density method to connect chiplets of choice and they're often connected to TSVs below them. And so what happens is that the TSV or the microbumps will be lined up on the face of one die to the face of another die, touched together, and then reflowed. For this reason, it's pretty obvious to see, or simple to see, how having bumps that are deformed by being probed a bunch of times would be suboptimal for the reflow process. So the challenges are basically related to the pace of the growth of pitch demand. So pitch demands are actually tightening faster than the halcyon days of Moore's law. Right now, we're seeing 50,000 plus connect in 1 centimeter square die, and we're actually have been 100,000s not too far away. So back in the days of Moore's law, we could at least count on a pretty direct correlation between transistor density and pad density and those and the tightening of those two pitches. But now that we are no longer dealing with Moore's law and unconstrained by that, people are chip manufacturers are asking to scale at a much different rate. And so the demands from probe and being able to hit all of the microbumps has changed dramatically. So with 2 to 4 times denser pads than a monolithic device, we're dealing with quite a significant engineering problem. Now, also, again, we have to always keep going back to that cost, because technically, and we have shown, and it can be shown, that you can actually run a KGD test and hit every single micro bump, but it's often far too expensive to do in a production setting. So one of the BKMs that we'll talk about is a hybrid bump and probe layout. And what this entails, as you can see in the bottom right, is a layout of 2 different probe types. In this way, we're decoupling the 2 requirements of different types of probes. In this case, IOs, fine pitch, and they can be fine pitch because they're lower power to drive signals at high speed. And then, well, if you can, we'll allow for more space for bigger probes that enable higher currents and higher power densities. By segregating them from onto the perimeter, the IOs onto the perimeter, away from the power and grounds in the middle, you're actually able to keep the job of probe easier, which keeps the cost of your probe card down. Now, this does require some flexibility on the part of the wafer designer, but if it's possible, it's certainly something that the 2 designers can communicate in order to keep the costs down. Another reason for doing this is actually not even in cycle time, but as far as downtime. The reason that we use a higher pitch probe for the powers and grounds is because a lower pitch probe allows for higher current probes, and these are less likely to burn out during high current testing. During a high current test, if a probe exceeds its maximum allowable current, it will plastically deform and fall, and the probe tip will fall out of plane with the other tips in the array. If you might see, for example, a probe deform 10 to 20 microns, and this product might have a planarity spec of 10 microns itself. This basically entails a costly downtime event to either repair the probes or find a new, design the test around not using them. And then here in a specific example is that you can see by using a 130 micron pitch probe versus using all 80 micron pitch probes, you're also allowed to get better power impedance by using the higher allowable current probes. And another one of our favorite ones to talk about is employing test pads among the microbump arrays. Designers can integrate dedicated probe pads within the component die to enable the use of traditional DRAM cantilever probe technologies. This allows full wafer contact, which allows for much higher parallelism and therefore a lower cost of test. One of the other benefits is that it avoids directly touching the microbumps. So as we discussed earlier, it'll keep the fidelity of the bumps higher for when they reflow to each other later on, and increase or decrease the chance that the final product will have to be scrapped for reflow reasons. And finally, because these dummy pads actually aren't ever going to get reflowed themselves, you can relax the constraints on size and on pad damage. For example, you might be able to probe it 10 times and not worry about how it bonds later in the future. This one actually requires considerably more effort and flexibility on the side of wafer designers, and it also costs more space. So this is sometimes a hard sell for different wafer designers. However, the higher parallelism enabled from full wafer contact makes it worth it if it's possible. And so in conclusion, we really want to kind of explain that the increasing test complexity and coverage is unyielding, and to, if when possible, relax the demand for KGD. KGD exists as a good ideal or nirvana or way of hypothetically referring to costs, or referring to yields and fault rates of fault. However, it's depending on the product and depending on the yield, it's possibly not the best thing to go for. So we went through two specific examples of die and layout strategies, but we also want to mention that there are several other strategies, that there's actually more illustrations of a mentality that we should have when we're approaching probe and wafer design. Other ones that I did not touch on that make a lot of sense would be, can you touch on multiple microbumps with a single probe? Like for example, can one probe touch 2 powers or 4 powers and grounds, or powers or grounds? For perhaps you hit only 1 out of every 5 bump while using built-in self-test and design for test to make up for the loss in test resolution. Also, you could also reduce the compliance for overtravel requirements, especially with a full wafer contact card. To achieve perhaps 100 micron overtravel, you're asking the probe card to compensate for all of the planarity differences within the wafer, tester, and possibly chuck on the prober as well. Again, these are not a fully comprehensive list of things that we can do to save costs on probe and keep your ROI high. But this is an illustration of the mentality that we should have and the ways that we should guide our discussions between wafer and probe designers. And with that, I'll open up for any questions.
Thanks, Will. So I'd just like to remind folks to put your questions down in the Q&A button at the very bottom. So feel free to add. But yeah, we have a few questions here. So okay. Maybe the first off the bat, I guess in the last slide 7, if you could go back there real quick. Mm-hmm. So the question was, how large are those test pads? And what sort of keep out zone do you need around them as well? How much area is that consuming?
Well, so these test pads might be, I guess the ones that we typically see are about 40 to 50 micron. I mean, these are high density arrays. And so people don't go crazy with it, willy-nilly making big pads everywhere. But, if possible, the idea is to make it as large as you will be allowed, right? Right. A part of the engineering challenge too is that we have to reach over, that the probes have to be elongated slightly to reach over the bumps. So it does require a bit of give and take and conversing with your probe designers and between wafer designers.
Got it. The other, I guess, corollary to that is another question. I think it was on page 6 or 5, I believe. Go back there real quick. Yeah, this one, page 6.
Okay.
Yeah. So as we have a mixed or hybrid bump kind of layout, are there any sort of spacing rules that you have to put in place between a high power probe versus a high speed probe at that boundary between the two that we have to watch out for?
Between the two, you mostly just need to respect the pitch demands of the higher pitch probe. So you can imagine that the 80 micron pitch probe, you have 80 micron pitch probes on the perimeter and 130. So, the BKM there would be to keep the IOs 130 away from the 130 microns away from the powers and grounds in the middle.
Right. Okay. Let's see. Another question, when you say KGD, do you mean singulated die? Is that right?
Yes.
Okay. Easy answer.
Keep them coming.
All right. So let's see. I guess, so the question was, do they get covered with passivation after being probed? So I guess we're more referring to the test pads, I think on page, it was 8, I think, 7 or 8.
Yeah.
Yeah, 7. That's right.
So like, I guess kind of the interesting thing is that it actually doesn't matter to us, right? I mean, we're talking about design of the layout. So this kind of fits in with my comments about how we can relax the constraints on damage. So you could passivate over it after it's been probed, or you could not, and you would still be able to basically run the test exactly the same if you chose plan A or plan B.
Yeah. Okay.
So that's
what are they? Yeah. So what's, I guess, the state of the art kind of a minimum pitch on these microbumps from what you've seen from the industry today? How small can we go? And what is the limit that you think that we can get to before we run out of gas?
So 40 to 50 microns, or just, I guess, right now we're creeping under 50 micron pitch for microbump size. The microbumps themselves are perhaps maybe, at least in this picture, 25 micron diameter. So that's a certain limit. So as long as you obviously can't go smaller pitch than the size of the bump themselves. So that's kind of your threshold there. But we all know that that's not going to be the end of the story. So there is already basically trying to bond without the bumps and just TSV to TSV in the future. And that kind of approach will probably require a lot of, this kind of gets more into chip manufacturing, but it'll probably go away with, reflowing and an infill, and just use just bond TSV to TSV and stack those chips right on top of each other, which is a different sort of engineering challenge. But as for probe, the problem will basically be the same, that we'll be presented with TSVs and at fine pitch, and they'll just be a smaller pillar. And so I would love to find that there is a terminal pitch or an asymptote, but we thought we had one when Moore's law ended, and it didn't seem to be the case.
They keep pushing.
Yeah.
Can you elaborate a bit more, I think, on the hybrid bump strategy and really what some of the key benefits of that hybrid bump strategy? Yeah, back on this slide.
So probe burnout is a real problem when, especially during the high current testing. Perhaps some products might get tested at 10 times the current of their actual use case. And what often happens is not only is that 10 times, perhaps the probe and test might be designed for that 10 times, but a faulty die and the way that it is faulty might cause a short and might charge it even a higher current than even the 10x that you were allowed it to have. So in that case, you really want to use the largest pitch probe that you can, or like a wider probe with space between them to allow for higher power. And then if you have a larger probe, then you can also achieve better power impedance as well. And then you asked me to kind of talk in general. So the other benefit is that, I'll repeat, I guess, just that, by separating them, if you were to have the IOs and powers and grounds all scattered about with each other, then the circuitry on the probe card would be more complex, and then therefore it would take longer to receive, and it would cost more.
Okay. And just a reminder for folks to please put your questions into the Q&A window. It's just a lot easier to manage in that window if possible. All right. So one question around the space transformer design for hybrid pitch. Are there additional complexities, or is it simpler? Does it simplify kind of that brick that has to kind of hold all these probes, or is that designed any differently?
Yes. I mean, it is a massive challenge. I guess that's kind of what I was talking about when I said that if you can segregate it, then it makes that circuitry of the space transformer easier. So that's a certain reason to have a goal of doing that. So if you can you combine powers and grounds, then you can kind of if as the test and product allows, then you can combine some of the circuitry of the powers certainly together, or in some of the grounds together. And if you don't do that, then the circuitry will be more complex, and your space transformer, which drives a lot of cost of the probe card, will be a lot higher.
Okay. Was there a limit in the maximum number of bumps that can be touched down or tested in this hybrid bump kind of situation? Or have you experienced a certain limitation in the total number of contacts? Or what drives the limitation, I guess, maybe is another question.
That's a great question. So there are a couple of factors. A repair event. So the likelihood of a repair event is a reason not to scale. Perhaps if you burn out a probe in the middle of the array, and you have trouble getting to that probe, if it burns out, is a reason. With a large, if we're talking about vertical arrays, the physical like X and Y dimensions are a limiting factor, because some of the mechanics of the interplay between the probe and the guide plates and the space transformer, the tolerances scale and stack up. And so as the product gets larger and larger, the tolerance stack up around the edges kind of becomes problematic for alignment. So to maintain good C-res and good probe mechanics, it's better to not really live on the edges of your X and Y size.
How many bumps have you seen in terms of a limit?
We've seen like cards that have well, definitely deep into the tens of thousands, 20 to 40,000 probes. And on full wafer contact, we might be talking on the order of maybe 180,000 probes. But but those are different technologies. So in a full wafer contact, you might have up to 180,000 probes. And then on a vertical array that has to move around with more fidelity but lower parallelism, you might see about 10 to 40,000 probes on the ambitious designs and the high density high hybrid probe layouts.
Thank you. Let's see. So who are the major fabricators of these microbumps on silicon that you see today in terms of manufacturers?
Oh, well, so as I work for a specific company, I don't feel too comfortable getting into too deep, okay. But, the big players are, the people who have, I can just name people who have HBM or HI products out in the field. And so they do include the likes of TSMC, Intel, and Samsung, and others.
So what is from what you've seen so far in hybrid bump and high speed kind of probe technologies, what is the data rate limit or the bandwidth limit that you've typically seen for some of the more high speed type probes, either single ended or differential? Is there a specific limit that this technology would support?
I'm not familiar with the upper thresholds. I do know that we have performed, KGD level tests with, through microbumps at 3.2 gigahertz. But I couldn't tell you that is an upper threshold or a limitation, but it has been proven that to be possible, that you can probe every single microbump and at full speed and determine KGD. The cost and time in that experiment were non-factorial. So yeah, it's possible, but not economical.
Right. And I think there was some talk even yesterday about known good stack testing a little bit. Does that change any of the rules of the game that you've seen or that you might predict in this region? Or a bump is a bump is a bump, doesn't matter, stacked or otherwise?
I'm not sure what you mean. A bump is a bump is a bump.
So if we're touching down on a stack versus a single die on a wafer,
Okay.
Doesn't change the roles of the game, I guess, in any way. From a probe card.
No. Yeah, I would say no. And from a probe card standpoint, no. But from a cost of test, which is really, I guess, impossible to decouple, I would assume yes, right? So, and then that kind of comes down to one of these trade-offs that we're talking about of, do you assemble them all and then test them later, and so on and so forth. So I think to answer your question from engineering of the probe card, a bump is a bump is a bump, but the actual answer is going to come down to how do you want to run, perform wafer tests, and as a process, which one is the smarter thing to do? And those are more or less impossible to decouple. So from a probe test standpoint versus a probe card standpoint, a bump is not a bump.
Fair enough. All right. I think that's probably all the time that we have at the moment. So thank you, Will. This is awesome.
Thank you.
And, lastly, I want to thank our sponsors again. Our diamond sponsor, Amkor, with differentiators in technology, quality, and service. And Advantest as our emerald sponsor, receiving the highest ratings in the annual VLSI research customer satisfaction. And lastly, I would like to thank all the presenters, the panelists, and most importantly, everybody who attended that made this a great event. And I look forward to seeing you at a future event, either here online or in person. And I will wish everybody a good rest of their day. Thank you.